Going on. 3, 2.
Afternoon, everybody. Welcome to the 74th edition of the How Do You Know program. I'm Dr. Daniel Barth, and this program is brought to you by the Star Mentor book and by the Explore Alliance. So if you are a new astronomer or no one, we encourage you to pick up a copy of Star Mentor. If you already have your copy, drop us a review on Amazon. That always helps. And the Explore Alliance, of course, for all your science and tech needs. So let's talk about today. This is another check the box. Something I've always said in my astronomy classes. People will ask me, well, what about this cutting edge issue or the other? And I've said consistently since I've been teaching astronomy that I thought that Venus was a volcanic place. The hottest planet in our solar system because it traps heat with the infamous greenhouse effect. A carbon dioxide atmosphere, 96% CO2, so very rich, almost pure CO2 atmosphere, and a heavy layer of clouds from a lost ocean. Both of these help Venus to trap heat and make it a quite lovely little hellscape. Temperatures on the ground around 850 Celsius, something silly like that. Just ridiculously hot. Many metals would be molten. You could step in a puddle of solder or lead or sodium. It would be a very nasty place to be. And we know that from surveys of Venus with the Magellan spacecraft, which was a 1990 effort. So that puts it about 33 years ago. Magellan located more than 1,600 volcanoes on the surface of Venus. You think about that. How many volcanoes can you name on the surface of the Earth? Perhaps 8 or 10? But we think about that and we're like, wow, goodness, 1,600 volcanoes. And that's big ones. That's big ones like Mauna Kea or Mount Hood or Mount St. Helens or Etna, Stromboli. These are big volcanoes like that. And a million little ones. So yay! It's the volcano theme park of the solar system. The only place as volcanic as Venus is the moon Io around Jupiter. But even that doesn't have this vast cadre of volcanoes. So the question is, gee, we sent this Magellan probe to Venus, and it was the most successful space probe that NASA had sent up to that time, and sent back a huge amount of data, over a terabyte of data. And they had all these photos, or images, I should say. They're not photographs, strictly speaking. They had all these images from the surface of Venus and all these volcanoes. And you're like, so Venus is volcanic, right? Well, and there the arguments would begin. And people have been debating about volcanism on Venus ever since we learned how hot it was back in the 60s. So about half a century, we've been arguing about these things. And it's fine. This is like, heliocentric, geocentric back in the day. If there's no defining experiment, if there's no defining set of data that says, this theory, not that one, then we are just arguing. We haven't got enough information to solve the problem or to answer the question. So this idea, and a great many people, including myself, said, look at all these volcanoes and the hideously high surface temperatures. You wouldn't need to heat rock much to get it to transition to magma on the surface of Venus. And so you're like, well, with this kind of a volcanic landscape and these temperatures, it must be volcanic. But this is a deduction, not data. Deduction would do Sherlock Holmes proud. It is a deduction, but it's not data. And so we're like, it's not data. We need data. How do we get data? Well, one of the issues is the last spacecraft we sent to Venus that did extensive imaging. We've got a number of probes on Mars. We've got rovers on the surface. We have orbiters. We have high resolution cameras in orbit. We have internet nodes in orbit. We've got a tremendous amount of hardware bearing on Mars. But the last time we sent a probe to Venus was 1990, the Magellan spacecraft. And Magellan was very cleverly designed after the Venera probes from Russia, then the Soviet Union, after the Venera probes had gone ahead and landed on Venus and parachuted through the atmosphere and given us lots of data, NASA decided that a lander was not in the cards. But they said, look, we can send an orbiter that can image the surface of the planet and map it, and we'll do it with radar. So we can penetrate this cloud layer. The cloud layer on Venus, you're talking more than 50 miles thick, almost 100 kilometers of clouds. It's a very thick atmosphere, about 100 times the thickness of the Earth's atmosphere. And it's got this massive cloud layer, just kilometers and kilometers of clouds, and it's clouds 24/7 all year round. And so when we talk about this, we realize, well, you can't just sit in orbit and take photographs of Venus. It won't work. So what did they do? They used what's called a synthetic aperture radar. NASA speak, a SAR or SAR. And here they could send down radar signals and they could actually use radar waves like light and paint the landscape. And this synthetic aperture radar could get a resolution of 100 to 300 meters. And the probe's in an elliptical orbit, sometimes closer, sometimes farther away. So the resolution depended on how close you were. And when they looked, they found evidence of past tectonic movement, kilometers long lava channels, basically riverbeds for lava. They found pancake lava domes, which we don't have on Earth. These are places where the crust is soft, and essentially you're getting a large flat top dome, a lava extrusion or a lava flood. You get shield volcanoes like Mauna Loa, these large volcanoes with a very slow slope, and they obviously are built with very runny lava because they're not steep and peaked like some of the classic volcanoes, but rather they're a shield volcano. And a little bit of study and thought and mathematics, and scientists realize, wow, with a surface temperature around 800 degrees and this very high pressure, more than 90 atmospheres, Earth atmospheres of pressure at the surface, this is going to make lava on Venus very, very fluid and low viscosity. It will flow more like syrup than if you've seen some of these photos of volcano of eruptions on Hawaii, where you get the large sheet of lava from the volcano, and it's flowing downhill at some number of centimeters per hour, and it's relentless. It will destroy everything in its path. But this is more like this river of liquid lava. So we find that some 85% of the surface of Venus is covered in volcanic features. If you think about the United States, think about Europe, think about the country where you are, what percent of the surface of your locality is covered in volcanoes? I can say here in the Midwest, that would be 0%. We don't have volcanoes here. Farther out west in the United States, yes, certainly. And we have some very volcanic landscapes in places like New Mexico and things like that. And in Utah, where you can see evidence of ancient volcanic activity. But 85%, that's stunning. The other thing they took advantage of with the Magellan probe is the actual rotation rate of Venus. Venus spins retrograde. In other words, it spins backward compared to other planets. And as it spins very slowly. It has an orbit some 240 some days. And for the Magellan spacecraft, it would take 243 days for the planet to rotate underneath the spacecraft. And so the spacecraft, in its basically 90-minute orbit, would map out very thin slices. So it's like taking very thin slices of the planet and constructing a map from this and then beaming this data back to Earth where it could be all put together. And they took advantage of this very slow because if you get very thin slices, you can get very high resolution. And in fact, the slices all overlap each other, so you can get multiple photographs of puzzling data points, so you can see them from different angles, and that may help clear up what exactly that they are. So all the spacecraft up to 1990, right? So you think about the Mariner and the Pioneer program and all the various craft. All the craft up to Magellan had returned 900 gigabytes, 900 gig of data from photographs, from chemical tests, from magnetometers. All the different instruments had returned 900 gigabytes of data prior to Magellan. Magellan, during its lifetime, returned 1.2 terabytes of data. Now, it's just when we look at this, the crazy thing is when we look at all this data, there's 1.2 terabytes of data. Think about having 1.2 terabytes of photographs on a monster hard disk somewhere, and you're like, oh, I must look through all the photos. Oh, and let's not make it the real, like 10 and 15 megabyte photos from a high resolution camera phone. No. Let's make it low res, old school. So you're talking about just a flood of images, just a huge, huge number of images. And so 1990s, looking through all these images, not one image can they find direct evidence of volcanic flow. In other words, looking at these things, you may remember photographs from the Voyager spacecraft. And when they flew past Jupiter, one of the moons they imaged was the moon Io. And Io was imaged with volcanic plumes spreading out over its horizon. And when people saw these, the crowd went wild, as they say. And everybody's like, wow, this is astonishing. Look at this. It's an amazing, astounding volcanic activity happening on this moon as we watch. Well, that was the 1970s. Then we get up to 1990 and we have 1.2 terabytes of just Venus. Do we get one volcanic plume? One geyser? No, we do not. So no obvious evidence of volcanic activity. So there we go. Well, what do we do? Well, we realized that, and we've talked about this before. You and I, we've talked about this idea that old spacecraft, although the mission is over, um, people aren't done. The Voyager spacecraft data set, there are still scientists today poring over that data set, looking to discover new things. The moons of Pluto were all discovered by going back to old Hubble photographs. And we look at the discovery of Pluto's moon, Charon. And the scientist's name was Christie. And he went back over all of these photographs, and he found that, oh, there's this bump and it switches sides every 6 days or so. And so he announced to the world he had found Pluto's moon, and it came to be known as Charon. So we see this passing over old data all the time. The Magellan had given us over a terabyte of moderate resolution photographs. That's a lot. That's a lot of photos, my friends. And so we looked at this. It took, over the history of the Magellan probe, and you're like, oh, it takes 243 Earth days to see the planet once. So, what, 9 months to see the planet once? And it completed 6 of these complete mapping passes during its lifetime. And as it did so, for the folks back in 1990, the size of the data set was one of the real technical challenges. Now, we look today and we go, oh, gee, a terabyte of data. Well, that's not bad. I have my little hard drive here. It's about the size of a pack of cards. And gosh, this is a 2 terabyte drive. But back in the day, in 1990, this was not to be had. A 40 megabyte hard drive was a very large hard drive in the day. Consider a high end. This is a computer that a professional would buy for themselves. 4 megabytes of RAM, 0.004 gigabytes, boys and girls, 0.004 gig. A 5.25 inch floppy drive. With each drive, you could store up to a megabyte. And you would also have a 3.25 inch rigid disk drive. Those would also hold about 1 megabyte each. And we think today, when your phone says, oh, and you're updating your game, you're playing a baseball game on your phone and you update it, it's like, oh, 75 megabytes. And you're like, no, that would be 75 disks, physical disks to hold that data. This thing, 40 meg hard drive, 0.04 gigabyte hard drive. You know, today we have flashlights or flash drives, and we say, oh, here's a flash drive. And this one happens to be 32 gig. Okay, well, that's 32 gig. At the time, a 40 megabyte, a 0.04 gig was the big hard drive of the day. The processor, 386SX, operated at 1/3 gigahertz, about 386 megahertz. A 14-inch full-depth, full-size TV color monitor that was 1024 by 768, which is far below the resolution of any of your smartphones. DOS 3 and Windows 3. The cost, inflation adjusted, $4,600 today's money, about $2,000 in 1990. Digital imaging software did not exist. Things we take for granted, like Photoshop or even a quick photo editor in our phone, didn't exist. You didn't have the ability to process photographs that way. Photographs to take a look at, oh, here's multiple images from different angles of a terrain. Can we now computer process those and get a 3-dimensional map that we can then fly over? NASA does this with Mars photographs all the time. You've got all those videos. Oh, take a low-level altitude flight on Mars, and you're flying over all the canyons and the hills and the dunes, and it's very spectacular. It didn't have anything like this. So the problem is also when you're trying to upload and look at photographs, the transfer speed, the upload speed of the hardware is so glacially slow compared to what we have today. Ask an old person with no hair or maybe a white beard. Wow, do you remember loading up things like MS Word and Lotus 123 or something like that on a computer, and the disk would sit and churn for minutes to upload the entire program? Yeah, crazy stuff. Crazy stuff. And so they have these 1.2 terabytes of data, but what do? Go through one photo at a time? Um, that's billions of man hours. It's crazy. So, in fact, what's happened today? There's a fellow, Robert Herrick, at the University of Alaska, and he said, "Ooh, let's go back to this lovely terabyte-sized data set, and let's take some modern image software." And with his software, he can put the whole terabyte onto a drive, and he can say to the software, "Okay, go through and compare all the images digitally." Image comparison software is easily done. And he actually took a look at two sets of photos of the same area taken 8 months apart. So if you think of that 243-day circle right cycle, it's a first pass, second pass photo of the same location. And so he's taking a look and comparing the photos from the two data sets, which with modern computer technology you can do very quickly. And he's also able to take and have his modern software stitch all of these images into one large map that he can take a computer and scroll over and zoom in and zoom out. We all do this with Google Earth and Google Maps technology all the time, every day. And today it's in our smartphone. It's in a device that weighs a few ounces and fits in our pocket. This is the state of the art today. He's working on a very nice computer system, I'm sure. He's stitching these things together, but you could do this on a good laptop today. And he's also done something very special with this. He's taken multiple image sets of the same place, used them to create a 3D map, and then he's compared points on the two uh, taken from different angles, and he's asked the computer to what's referred to as orthorectify the images. And orthorectification means the images, the 3D image is processed so that when you tilt it and see it from the different angles, it shows it's accurate to the photographs that were taken. You also have to realize that the resolution of these maps quite low compared to what when someone says, "Oh, look at here's this panoramic photograph from NASA or ESA or JAXA," and we're expecting this brilliant high def thing that we can zoom into, and here we go, going to do the zoom thing and zoom right in and see amazing detail because we're used to a resolution of perhaps 25 to 50 centimeters, depending on a lot of the high rise orbiter on NASA, operated by the University of Arizona. That thing has a resolution of 25 centimeters. So you're talking a quarter of a meter versus the best resolution for Magellan is about 100 meters. Whereas they're taking these images anyway, and they're doing this orthorectification so that as we scroll over them and zoom and move the digital camera eye or point of view, that we get the best image. And what they were able to find, and they looked at basically one strip, right? They looked at one strip. Very very small amount, about less than 2% of the surface in this strip. And it's photographed twice, and they're comparing this. And they discovered, hooray, a new volcanic vent. So we're talking 8 months between the photographs, and they knew the vent was there. The vent on the first pass had an area of about 2 square kilometers. That's not insignificant, but in Venus, the theme park of all volcanic places, not anything special to write home about. So 2 square kilometers, and it was basically circular. And on the next pass, 8 months later, it's not only changed its shape; it's now kidney shaped, but it's also grown to doubled in size to about 4 square kilometers. So we look at this vent and we're like, wow, this is actively changing, and we're seeing more lava on the ground in a short period. And the vent now has a dark interior, which is thought to be a lava lake, the other stuff around the edges being solidified lava. And we absolutely have smoking gun evidence of current volcanic activity on Venus. Hooray! This is something Steve and scientists have been looking for 50 years and haven't been able to find. And it's not that the data wasn't there. You realize that the information was in this data set and has been lurking there since 1990, whenever this exact pass was taken. Goodness, it's been in the data set this whole time. But part of your ability to make use of a data set is your ability to process it. What kind of mathematical power can we bring to bear on this set of data to extract information? And we know that calculating, with a slide rule or a calculator is very laborious. And in the time of 1990, scientists were looking at poring over this huge data set of photos basically by hand. There's Sentil. Hello, my friend. Glad you've joined us. And so they looked at this vent and they realized, oh, and this makes sense that it could spread this much in this much time, because we know that the lava is very very non-viscous. It flows probably more like syrup than regular what we think of as magma. And so they said, well, could this be something different than volcanism? Could it be just tectonic activity or something? And so they said, we will try to find a non-volcanic explanation, something. And so they fired up, again, big computers, things that weren't available in 1990 at all. And they decided to run, they said, here's an original volcanic feature, and let's run simulations on it to see if we can get it to be twice its size, twice its area. And we'll run these things and we'll keep running them. Will we, in fact, be able to get simulation where this occurs from non-volcanic causes? And they ran hundreds of simulations, lots and lots of hours of computer time. And they were not able to find anything that made this work except volcanism. And so you're looking at, they covered in their study, Herrick and his people covered less than 1.5% of the surface of Venus, which is crazy. It means there's there's room for a lot more research. And we think about this, we've only covered 1.5%. The vast majority of things are undiscovered, and undoubtedly lots of interesting things in that data set already for us to discover. We're not done with Magellan yet, which is stunning. I would bet that Magellan is older than the number of people watching this program. But nevertheless, so where do we go from here? Where do we go from this point out? We're getting new data, and Venus is finally, the debate is settled. Is Venus volcanic or not? Today, yes, it is. So where do we go from here? Coming up coming attractions. In the 2030s, may we all live to see it, is being described by NASA and ESA as the decade of Venus. And NASA is preparing the Veritas probe. And you know, NASA folks, they love their acronyms. So Veritas is Venus Emissivity Radio Science INSAR Topography and Spectroscopy. That's what comes out as Veritas. And Veritas will be studying Venus's surface from orbit. And whereas the HiRISE, which is a early first decade 2000s camera on Mars, can photograph 30 centimeter areas about the size of an average dinner plate, well, guess what? The new probes will be capable of finding centimeter size changes. Think of that. From orbit, centimeter size changes. So you're holding your fist like this, you're holding your fist like this, and they can detect it from orbit. This just gives me pause. Nevertheless, and we're able to send this to another planet and work that magic there. So they'll be studying Venus from orbit, and along with Veritas, which is basically it's an INSAR. It's a synthetic aperture radar probe like Magellan, but 30 years up to date. And NASA also has the Da Vinci probe, yay, the deep atmosphere Venus investigation of noble gases, chemistry, and imaging. So there we go, the Da Vinci probe. And Da Vinci will be orbiting. There will be multiple components. There will be an orbiter component, and there will be an atmospheric probe component. And the atmospheric probe will go down into Venus. And there's been various things talked about. There's descending lander probes. There's parachute probes. There are dirigible type probes being discussed, right? A balloon type probe that floats in the atmosphere for a long time. So that may be happening too. It's hard to say. And then they have another probe from our European friends, the Envision probe. And again, Envision is supposed to be able to look at centimeter size changes on the surface of Venus. And I'm assuming that Envision and the Veritas probe, like Hubble and Webb, are going to be operating in different spectrum areas. I can't imagine that the two of them would go, ooh, let's build identically spec'd probes. That would be a huge waste of money and effort. But you realize that until some of these things start launching, even maybe in 28 or 29 earliest, that's if everything goes right and the creek don't rise in the scientific community, right? There's not political upsets between now and then. There certainly will be, different administrations will be in power, and how they think about space exploration may change how things go. But we realize, we've got at best 5 to 8 years before any of these launch, and at best 10 to 12 years before we start seeing data from them. And until then, Magellan dataset is the dataset for Venus. You think about that. We collected it between basically 1990 and 94. And since it launched in 1990, and there were a number of delays, including the Challenger disaster, which delayed the launch of Magellan, we're really talking 1975 to 80 technology. So think about digital cameras and computer power from, the early 1980s. Quite primitive, vastly primitive compared to what you find on a modern cell phone today. Vastly primitive. So we're going to be launching this new set of probes in the 30s. But we think about this and we look at it and we go, wow, yeah, we're launching this new stuff in the 30s. But until then, we're going to be relying on a basically 30-year-old data set taken with 40-year-old imaging technology. And the crazy thing is that data set is not nearly all mined out yet, not even close, because bringing new computer technology to bear brings new information out from these data sets. And this is true of all our data sets. Uh, we are creating digitally in this century the great library of Alexandria of space exploration data. You think about data from the Soviet era, from early American efforts, European, the Japanese, the Chinese, and now, of course, there are wealthier nations in the Middle East. The United Arab Emirates has sent out spacecraft, and so India has sent out spacecraft. And so we get all these, I'm hoping I'm not missing anybody. But we've got this world community of space exploring countries. It's a much larger group than it used to be. And the technology is light years ahead. If you compare those specs I gave you of a typical 1990 computer, and a powerful one at that, and you compare it to your average, $400 laptop from an online store, and you look at the specs and you realize, wow, that cheapo $400 laptop does a lot more and powers of 10 more than what we were able to do at the time. And both the processing power, the upload, download, and transfer speeds, right? The speed at which we manipulate data, and the sophistication of software, and the improvement of sensors. So we've got these four fronts on which we are improving significantly. So the decade of Venus should relay to us a great deal of information. And they're talking about the possibility of rovers tough enough to rove on Venus. Wow, I can't even imagine what that technology looks like. Anyway, friends, that's where we're going to wrap up for today. Thank you for joining us for another edition of How Do You Know? If you don't have your copy of Star Mentor yet, we urge you to pick that up. Amazon.com and any good bookstore has books from Springer. And go ahead and pick that up. Drop us a review, please, if you've read it or if you have a copy. And we will see you next week at this time, 4 o'clock Central Time, here on the Explore Alliance channel, when we'll bring you the 75th episode of How Do You Know? If you have questions or suggestions for a program or something you'd like to see us take up and discuss, write to me at astronomyforeducators@gmail.com. And all those emails do get replied to, friends. Thank you very much and have a great week. Bye-bye now.